Hello to our second segment of Oracle Database Architecture. In this section, we are going to describe and review the database architecture for a container database. A container database is the new structure for 12c, and it allows us to not only manage multiple applications within the database, it kind of allows us to have some separation between the management of those applications, how the data is organized and managed, and how the security deals with the data, while we still have one database. And in all of the operations, you only have to manage only one set of resources for all of the containers. So let's get back to our picture here of a single instance standalone database. If you guys remember, in the single instance database, we said that the database had two parts. Has the instance, which performs all of the logical work, and the database, that is a set of files that we use to make sure everything is in sync in the database and all the users performing their actions. In the instance, we have our shared memory, the SGA, the system global area, or as it used to be called, the shared global area, and the shared memory components. First, the shared pool that we use for management of the SQL, our buffer cache that we use for block management, and we have to create a buffer cache for each block size. The redo log buffer that we manage for the instance recovery and have the redo for database and instance recovery in case of a crash or a failure or corruptions. Then our large pool used for some database operation like the recovery manager, like parallel processing, communicating to the storage management instance, the ASM, and for the shared server managing the user global area. The Java pool for the JVMs and the stream pool for their application. Then, on the background processes, we mentioned that in the instance we have a bunch of background processes. Background processes are sessions that database runs and manages internally to keep the logical data and the physical data in sync. As we said, all the work happened to data logically, and the database is just a physical location where all the data is stored. So we discussed the background processes and what do they do in the previous segment of the standalone database. And then the database files that we use for database management. We talked about the control files because it is multiplexed that holds our database structure, all of the database operations, and the RMAN or recovery manager's repository. The redo log files managed in groups because we rotate between the groups, and multiplexed within the groups to better manage redundancy for protection. And of course, our data files that are associated to our table spaces. We talked about creating a copy of the redo into the archives, performing it for the recovery aspect. For the start of the instance and the management of our system operation, we have our parameter file. And then we talked about a security file called the wallet, where we have the server certificate, the keys, whether for SSL public key or for the transparent data encryption, database master key that is stored in that wallet. All right. On the client side, we said that clients connect to the instance because all the work is logical. The client finds a listener that is responsible to make the connection, and the database will register its services and every service and connection type that they support with that listener. To find that listener on both ends, whether the server side or the database side or the client side, we go through a SQLnet.aura that describes our network environment, and the TNSNames.aura that gives us our connect strings for each service. Okay? That will then point us to the listener. The database, we talked about PMON registering the database with the listener. Therefore, going again through SQLnet and TNS names. PMON would find the local and the remote listeners based on their name, and the default listener at 1521 who would register with. And then that listener would then know where this database located. It can produce the server process for the session. Once that server process is spawned, assigning a PGA for that server process, the server process communicates to the instance and gets connected to the user process on the client machine. So now we have a session. And the session is when the client communicates through the user and the server process with the database. Finally, we talked about our PGA that had two components. This was the private global area or program global area, the private memory for each server process where the work is done. Two parts, the UGA, the user global area, that has our session information, and the work area, where we actually open blocks and perform the work. Now, we talked about the shared server environment, where multiple server processes work and manage, share the same session. Since now they need to share session information, they would not be able to hold the UGA, the user global area that has my session information, private. Therefore, the UGA would relocate into the large pool, so now multiple server processes can share that session information. So, in a nutshell, we just did a quick review of the standalone database. Let's see how does this differ with the container database. So, as we said, a container database is exactly a single instance database, or it could be a rack. Okay? The type of database used really all compatible with each other. Okay? In this case, for simplicity, we're going to use a single instance. In the single instance container database, we still have our normal standalone database. That means I have my instance for that database that all the work is done, and the main database that has my control file, that has the redo log files, and has my data files associated to my system operation. Okay? And of course, very important to remember for the container database, the undo, which over here, we want to make sure that it is very well maintained for the database level operation. All right? So, as we said, a container database now allows us to have separation when it comes to management of different applications. Okay? So, when we build this database as a container has to be built brand new. Okay? You do not migrate a container. You do not make a non-pluggable database or a non-container database. You do not convert it into a container. Container is a shell. Has to be built on its own. So here we have built a container that has the instance and the main database. Okay? Now, in a container database, to be able to understand the different components, they call every component a container. Okay? And based on the container ID, they identify each individual containers. The container database can hold pluggable databases. Okay? Now, what is a pluggable database? A pluggable database is a database service with independent file system for data files, okay, and provide separation between the pluggable databases. Okay? So basically, all it is to have one container that can hold all of these individual schemas. Now, in the past environment, in 11G, in 10G, in 9I, what I needed to do is, if I needed individual applications managed on their own, totally independently, where I have separation for the data access, for the user management, for the file environment, I had to create an individual database for each one of those. So let's say I have 10 independent applications. In the past, I needed 10 databases, one for each one. For each database, I needed an instance, I needed a set of background processes, and of course, my data files. Now, the data files we're going to keep separate, so that part is fine. However, having redundant or 10 redundant set of background processes and 10 redundant SGA is very wasteful of our resources, especially where in the database operations, sometimes applications don't have a lot of load. And all of those resources could be wasted, where other applications could then use those information. This becomes very evident in how much resources, how much company resources in general can be saved. For example, in the test and development, we could run 100 different test environments. In the past, I need 100 different instances, one for each test environment, so I can customize and test not just the application, the code, the structures, and everything else. Here, I can create one container database. Of course, I need a little bigger server with a little bigger resources, because now it's going to support all of those different applications. And then I can put all of those test environments inside a single container. Provide autonomous operation for each application, where they're completely independent in their management, and save me a lot of resources by not having a lot of redundant processes and memory configurations. All right? So, all that said, now we understand that the purpose of a container database is to just provide that separation between our applications. And as we said, for the applications that I do want that separation, we would create what is called a pluggable database. So now that we understand the definition of a pluggable database, let us continue now to what that container database would look like, okay? And what exists separately for each container database. For the container database, again, we have one instance and one main database, okay? That means one set of control file that manages all of our database operations, the database, main database structures, and all of our recovery information. We have our redo log files. Remember, the redo log files are about instance recovery. And since I only have one instance, I can only have one set of redo log files. And by set, I mean one set of groups, okay? So I don't create redo log file groups for each pluggable database. There is only one redo log file groups for the container. And then, under the data files, of course, the container has its own system files. So let's write them here so we can see. It has its own sysaux. Okay, that's system auxiliary and the system file. Okay, what is stored in the system file? As you all know, this is the main data dictionary where all the metadata is stored. Sysaux normally holds our historic operational information. Okay. Then we can have, very important, the undo. And for undo, undo is related to transactions. Remember, we use undo for rollback process, for transaction management. And transactions are based on sessions. Each session creates an independent transaction. Sessions belong to the instance. You follow where we're going? There is only one instance. Therefore, in a pluggable database, there can only exist one set of sessions, no matter which pluggable database I'm going to connect to, because I can connect individually to the pluggable databases. The system would make it look like I'm connected to an independent pluggable database. However, you're actually connected to the container instance. Okay? All the sessions, regardless of the pluggable databases, as we talked about, since there is one instance, belong to this one instance. Since the session belongs to one instance, there can only exist one undo. Okay? So here we have the undo in the container. And then, of course, for managing our main system operation, we may need to do some temporary work. So here we have our temp table space and the temp files. Now, in a container database, the pluggable databases can share only the temp file from the container by default. So if a pluggable database, as we see in the little bit, does not have its own temp, then it will use the temp from the container. However, it can locally have its own temp and have an independent file system for temporary data management. All right, so now we can see here is our main container. Then, since we only have one set of redo, the redo for all pluggable databases will be contained within these files. And since all the redo is contained within these files, we will only have one set of archives. Therefore, all pluggable databases must share the same archives. There is no separation at the file level. Individually, at each archive level, because of the row ID, where we know where the row exists, in which table space, we know which pluggable database the table space belongs to. Therefore, at the data level, we know where the data belongs to. So use of the redo, when we are going to apply it by reading it, we know which pluggable database the redo would be applied, except all of the redo are combined in the same file, and they all will be in the same archives. Since there is only one instance, you would normally have one main wallet that will have one database master key in it. It will have one public key for the client communication, and of course one certificate for the container, since the users connect to the container. And since there is only one instance, there is only one parameter file associated to that instance. All right, as we'll see in just a little bit, the containers manages all of the parameters for the instance. However, each pluggable database will have its own set of parameters that can define how that pluggable database operates. All right, now that we understand the container and the components of the container, now we need to move inside the container. Okay? Now, what do we put inside the container? Inside the container, we put pluggable databases. Okay? Now, to be able to create a pluggable database, I can either take a non-container database, like the old single instance, convert it into a pluggable database, and then I can plug it into a container. I can build a container database by hand using create pluggable database, and then specify all of the options that I need to create that pluggable database. Or I can use an existing pluggable database and clone it and build pluggable databases just like it. So, to be able to build and start with a cloning, we give you a template pluggable database that is created by default inside the container. The template is called pluggable database seed. And as it sounds like, it is a seed for building other pluggable databases. This seed pluggable database is read-only. That means you cannot make any changes to this seed database. You can create another pluggable database using the seed. Then you can customize the pluggable database you create. Okay? And then you can use that as a template for building other pluggable databases with your specification. So here, we have a bunch of options of dealing with how the pluggable databases are maintained. Now, as we said, within the pluggable database seed, we do not have any authority to make changes. Therefore, in the pluggable database seed, we have the system file, okay, the system tablespace and the system files. As I told you, each pluggable database has its own independent set of objects, okay, and manages its own files. To do that, it has its own system tablespace. Since the objects and the code that used on the object can only be seen within this pluggable database, the pluggable database also has its own sysaux. That's the system auxiliary, where we store all of the historic SQL and all of the historic executions that are associated only to the data within the pluggable database. Okay? So, this is our seed database, and basically has just the basic structure of creating pluggable databases. And then, of course, we can build other table spaces, and data files will be created within the pluggable database. The relationship between a pluggable database and a container is associated using file name convert. Therefore, when you create files based on the file name convert associated to each pluggable database, we know where the files to be created. So you can use Flex architecture and automatic file management with an Oracle database. It knows where to create the files associated to each pluggable database. So next, let's say I create a pluggable database, call it PDB1. Okay? When I create a pluggable database, I can use this as a template again. I can use SQL. Or maybe I had an older 11G non-container database that I've converted into the pluggable database to plug in. So let's draw here also PDB1. So this would be my pluggable database, PDB1. Okay? Now, let's say I create PDB1 from the seed. Therefore, from the seed, I'm going to copy the system tablespace and the sysaux. Okay? Now, to deal with the temp, as we said, we have a choice. I can create a temp here locally, or I can use the temp from my CDB, from the container. Most of the time, you do want to create a temp at the PDB level. Remember, these are applications that do sort, that do a whole bunch of operations. And I want to make sure that if PDB1 users are performing sorts, I shouldn't really use a file that PDB2 users are using for sorts. Okay? Remember, when two groups use the same temp tablespace, the same temp file, now you have I/O contention. Okay? By separating the temps, you remove that I/O contention. So we strongly recommend for you to create temp files at the PDB level. And then for my other data, so I could have tablespace, for example, HR that I create here. I can have my tablespace sales, okay? So depending on what application data do I want to put inside PDB1, okay, I will go ahead and create the table spaces to hold this related data. Now, here I created a table space for HR and for sales, assuming the two are related to each other. Okay? So if the two data are related to each other and used together a lot, even though they may be separate applications, you do not want to put them on a separate PDBs, because PDBs can only communicate to each other using DB links. Okay? And having to build database link between PDBs can actually introduce a layer of overhead in your processing and data management. Therefore, if two schemas are strongly related to each other and data between the two schemas are accessed together with this type of close relationship, it is best to put them inside one PDB. If the schemas are different, for example, here I have HR and sales, but let's say sales is not a schema that would relate to my HR that much. However, I may have another application that is called, I don't know, employee benefit. But the employee benefit, of course, is based on the employees in the company. Therefore, employee benefit schema could relate directly to the HR schema. So I would put that in one pluggable database for much better management and much more effective speed and data management. So I would put them in the same pluggable database. All right? So now I have created a pluggable database, and then we have our PDB seed. When these are created, by default, a database service is created in the name of these particular pluggable databases. So now I have a service for PDB1 and I have a service for PDB seed. Since these services are automatically built in the database, then they're also automatically registered with the listener. So now my listener also knows that these PDBs are being served by that container database. All right? Now, coming back to our PDBs, as we said, our sessions belong to the instance. And when you start a session, all of the options for your session and all of the setting for session management by default will copy from the parameters and the settings in the instance. However, maybe each PDB has a different requirement for the SQL execution. Okay? Maybe in one PDB, I need to set, for example, optimizer mode to first rows, and in another PDB, I may need to set optimizer mode to all rows. Okay, so this would be in a PDB1. This I need for PDB2. However, since I'm holding different values for the same parameter inside a container, these parameters cannot exist here in the parameter file, because over here they're only executed at the instance level, and then they become my database default. Therefore, I cannot have multiple defaults put in there. So what do? We have moved all of the associated parameters that you can use at the PDB level to the PDBs. And the parameters for the PDBs are stored in the system file of each PDB. So now, when I set optimizer mode for PDB1 to first rows, that is stored in the data dictionary of my first PDB. If I set optimizer mode to all rows for PDB2, this will be then held in the data dictionary of the PDB2. So when the users connect, now these parameters becomes my PDB default. These parameters become PDB2 default. If PDB does not have the parameter, then it will pick up the default from the CDB, from the container. All right? Now, of course, within the session, if the user has altered session privilege, then the user can change the session information. Okay? Because I may have an application that requires two different types of sessions. One session for reporting, one session for transaction management. Okay? Therefore, I may have logon triggers or some other means of adjusting how these sessions operate. However, the default values for the general session associated with the PDB and the PDB management, all of those parameters are in the data dictionary of the PDB, in the system files of the PDB. So now we can see the architecture of a container database. Okay? And as we cover in the classes for the container database, the management and dealing with the container database is a little bit different than dealing with our non-container database like the way we used to do back in 10 and 11. For example, when you create these PDBs, the services in the database, as we said, is automatically created. And those services are automatically registered. With the listener. Okay? That I don't need to do anything. When you create a PDB, all of that work is automatically done for you. However, on the client side, the systems do not automatically update our TNS strings. So if now a client wants to connect to PDB1, on the client machine, that PDB1 service is not built in my connect strings. So then we have to manually add connect strings to the PDB. Okay? So we have to manually create those connect strings on the client machine to be able to now identify the services for the PDB and then connect to the database under that particular service. So just a quick review. The container has the main database, my instance, and the main database, has the redo files, has the undo, and has the control file. There is only one set of these files existing at each container because that manages my instance and all of the database operation. Then for the pluggable database, again, they manage schemas, they manage a set of related objects. Therefore, I have independent containers with the DB file name convert. We have specification of where these files are located and are managed. And then for each PDB, we have its own associated files in their own location. PDBs have their own parameters that is stored in the parameter file, and it now provides us with the type of configuration that we were talking about, where I have specific instance that is built and the container that is built, and then inside of it I have these independent services that are created. And one thing as a DBA we should always remember, even though we call these pluggable databases, they are not really a database because they do not have an instance. Okay? They do not have a physical database like the control file and the redo log files. Therefore, they are a service inside a database that have become independent for file management and operational management. Now, to be able to manage our pluggable databases are completely portable. So I can unplug a pluggable database from container 1 And when you unplug a container database from the container one, we create an XML files that describes this pluggable database. And we can then use that XML files to take this pluggable database and plug it into a different container. Now, when you unplug a pluggable database, you're actually creating a duplicate of it. You do not actually remove it. Therefore, if I want to create a test environment, all I got to do is unplug this, meaning create a duplicate of it within that XML specification, and then go to my test container and plug it in. Now I got the full test environment. And when you do unplug and plug, you can either include your data within that XML file, or if the data is big, we do not put the data in the XML file, we just put the metadata in there, and then we copy the actual data files to its location under the right name. Very similar as the transportable tablespace operation that we manage for the big file movement or movement of file between different platforms. So pluggable databases are managed the same way to make sure that we can easily migrate all of this information. There is only two things we need to remember that are very important as far as the DBAs are concerned. And that is, we need to maintain the main database, because without the main database and without the main instance, none of the pluggable database would be operational. So we have to make sure that container is properly maintained. Okay? Then the second thing that we want to make sure that we set up would be the specification in how the pluggable databases are managed. Are they managed as a single container, and we perform all of the major database management at the container level? Or do I want separation between pluggable databases, and then I have different DBAs managing each pluggable database? Okay? Since both configuration can be supported, if you are using a management at the PDB level, there is still some management required at the CDB level, because there are dependencies between the system file of the PDB and the system file of the CDB, of the container. Okay? You can kind of think of the system and the sysocs between the container and PDBs like a partition table, where my main partition is in the main database, and then the sub-partitions are on each PDB. If the main partition gets corrupt, the sub-partitions cannot be accessed. That's the dependency between the PDBs and the CDB. If I'm going to recover, or if I have a damaged system file at the PDB level, no, that PDB cannot be accessed. If I have a damaged system file at the CDB level, now the whole container cannot be accessed. Okay? And if I do recovery of any system file, whether it being for the container or the PDBs, I have to take the whole container down and bring it up to mount and perform that recovery because of that dependency. Okay? But that is the only dependency when it comes to recovery management of the PDBs. As we said, they do have separate file system, and then they can be managed that way. So the only thing that is left is, how do we identify all of these structures within the container? Well, simple. We now add the pluggable database name to the object name. So if I have a table space HR, now that table space is called PDB1 : HR. So the table space is now qualified with the PDB name. Now we know where they're located. When you create a table, so let's say now I have the HR.employees table, and when I go read the metadata for the HR, I can see that HR is now located in the PDB1. Okay? So based on this type of relationship and this type of naming convention, now we can see that everything is properly being managed by qualifying all the naming convention with our pluggable database name. So, as we can see, this will now become the architecture of a container database. And if I have 10 containers here, then I have 10 of these independent structures, and with one main container. So, now all of the component and the detailed architecture is on the board for the container database, as we can see, and the differences are very visible between a single instance database and the container. Now, always remember, a container could be a rack database. And if the container is the rack database, no difference. All it is my main database has multiple instances. But I do now have a choice. I can go to each instance and define which instance would access which pluggable database. So when I go set up my TNS strings, I can point applications to independent instances, or I can have application load balance, okay, for the pluggable database for the multiple instances in rack. So if this is a rack container database, a pluggable database could be associated to one instance or many instances. Remember, as far as the listeners and the instances are concerned, the pluggable databases will register with all the listeners for all the instances. The way we manage the connection is on a client-side connect string. Okay? So when we build the client-side connect string, as these have to be built by hand, then we decide within that connect string, do we want to enable load balance and a failover? Okay? And then the network environment can manage that. All right? So now we fully understand and can see a container 12c database. This concludes our architecture discussion for the container database.